In the last class, we discussed about this intersymbol interference or ISI effect, and this is not due to noise, this is due to finite bandwidth. And that we discussed in the last class, that means that previous symbol actually corrupts, that due to the finite bandwidth, the symbols that you send at the receiver side, there's a smearing, and actually it fills the symbol duration, say some TB, and finally it corrupts the detection of the next symbol. This is called the, and also please remember that ISI is not the noise that we discussed. So in order to circumvent this problem that we discussed, that it is that Nyquist has given some criteria for achieving zero ISI. So where actually the pulse shape which has a non-zero amplitude at its center, t equal to 0, and 0 amplitude at plus minus n TB, where n equal to 1, 2, 3. That means what I like to say a pulse, it may be any pulse kind of thing, say something like this. So at t equal to 0, I have a value 1, but at plus minus n TB, TB is the symbol duration, where actually this pulse will cross 0, the next pulse, then here at TB you will have a pulse, but here it will have 0. So that means at this position, when you are doing the sampling, you have only the effect of the current pulse. Similarly, when at t equal to TB, when this, so you are sending the bit over, you are sending the electrical pulses like this, then you at this point when you are doing the sampling at the detector, you have only the effect of this one, because at this point this one is 0, the all post and previous, all previous and all post pulses, effect of all previous and post pulses are 0. So so for the sake of 1 minute, that means that my pulse, this is my ET, okay, and that means at 1 by RB it will be 0 crossing, 1 by RB, 2 by RB, 3 RB, or TB, 2 TB, 3 TB, like that. And if I just do the Fourier transform of this one, then we know that it will be, that I told you that 1 by 2 of 1 by RB. Okay. So then it will be RB by 2, that is 0.5 RB. And here it is minus 0.5 RB. What is my bandwidth? Bandwidth is RB by 2. Okay. Bandwidth is RB by 2. So that means here you see, that means what here you try to understand that I like to send, so each if you see, that means the transmission of RB bits per second. RB bits per second means in 1 second you are sending RB bits. That means each bit so that means here you are sending 1 bit, here you are sending 1 bit, here you are sending another bit. So that means each duration is TB. So that means, and RB is 1 by TB, that means your bit rate is RB bits per second. Now for RB bits per second, basically when you are doing this thing, then RB bits per second, that means requires a minimum theoretical bandwidth is RB by 2 Hz. Okay. So when you are sending these pulses to a channel, that means for this one, at least you need this type of one. Okay, so sorry. So when you have this type of pulse, finally you are getting this type of response. So that means your filter should also have at minimum bandwidth should be RB by 2. Okay. So then this pulse will go. So that means the minimum bandwidth is RB by 2. If you have higher bandwidth, it's fine. Now the only pulse that means it would be if a pulse satisfying Nyquist criteria and also has minimum bandwidth. So that is only pulse is basically sync. That means my point is that you have to have only the minimum bandwidth is RB by 2 and you are sending RB bits per second, and also you have to maintain the Nyquist criteria, that is 1 by RB, 2 by RB, 3 by RB. There it should be 0 passing. Then that PT equal to sync T, that is the only pulses. That means that PT equal to sync of pi RBT. That means sync of pi RBT means that sync of pi RBT equal to 0, that means it is 1. And when T equal to 1 by RB, 2 by RB, 3 by RB, all other terms, then it is 0. Okay. So that means here 0 means when T equal to 1 by RB, 2 by RB, all these things. And then what about the PF? So the Fourier, so that means that this is basically this is the PT, and what is my PF? This is my PT, and this is my PF. PF is basically what is the width of the pulse is RB. So that we say pi of F by RB. RB is the width, and the strength is 1 by RB. Why the strength 1 by RB? Because what is this one? This is 1. 1 means this area should be 1. As this is RB, then the height should be 1 by RB. Then only area should be 1. So that means you have this. So that's why this 1 by RB term have come. Okay. So that means that this has a bandwidth of RB by 2, and that you can see in the figure. But the problem of this one, you will see that the problem of choosing this pulse, that the problem of choosing this pulse is that this pulse will start from minus infinity. Okay, and it will extend to plus infinity. So that means you have to wait up to infinity time to start the pulses. And also, if you disconnect somewhere, means if you just say truncate somewhere here or somewhere here, then you will have a ripple in the here. Okay, so that means that this is the problem, and also so that means pulses are not realizable. Another thing is that even if the pulses are realizable, the decay rate of these pulses, that means the way it, so this one, then this one, then this one. If you just take the one mod wise, means rather even with if you take mod of sync pi t, then actually this decay is in the rate of 1 by t, which is very slow. I want a higher decay kind of thing, 1 by t cube, 1 by t to the power 4. Okay. So the point is that sync of pi RBT decays too slowly as 1 by t. Now the solution is to find a pulse PT, okay, that satisfies equation 7.23. What is equation 7.23? That means that satisfies a pulse like this. That means it is t equal to 0 and it is t equal to some plus minus n of t. Okay. Now, also it should be realizable, something like this. That means that this one, but also decays faster than one. Decays faster. So Nyquist has shown that pulse requires a bandwidth of k into r by 2 with k greater than 1 and less than 2. That is little bit. That means rather if you can spend more bandwidth than the minimum bandwidth, you can do the thing. That means your RB by 2 is the minimum. RB by 2 is the minimum bandwidth. Okay, rather if you can spend, that means RB by 2, that means k into RB by 2. Here if you see that it is k is between 1 to 2, that means between RB by 2 to RB, then actually this is possible. Okay, for that what we are doing, that means say let Pt equal to the pulses and Pf is the frequency, and Pf, the Pf, this is my this Pf, this is in the range of RB by 2 to RB, because I told that it is k is between 1 to 2, that means k1 means it is RB by 2, k2 means it is RB, that is RB by 2 to RB, and that Pt that satisfies that one, that means that it plus minus nRB, there it will be 0, and if I just multiply that means if I just define P bar T, another one where I am defining Pt into delta TBT. Okay, delta TBT means I have a, so what is P bar? P bar T is I am saying it will be so this is my Pt. P bar T is actually what I am doing here, then 1 by RB, 2 by RB, 3 by RB, I have an impulse. I am multiplying with an impulse. Okay, and rest of, so then what will happen? Then if I just multiply these two, and this duration is 1 by RB, that is T. So then finally you will have only delta T. If you just multiply with this thing, this term is 0, this term is 0, this term is 0. So you have only delta T. Okay, delta T into 1 delta T. So that is you are getting the P bar T, that is delta T. Now if I do that means P bar T is the sampled pulses. Pt is the continuous time pulses. P bar T is the sampled pulses, sampled at 0, TB, 2 TB, 3 TB, like that, minus TB, minus 2 TB, 2 TB. Okay. Now if I do this thing, that means what is the Fourier transform? If I just do this Fourier transform on both sides, that means Pt delta, so these pulses, that delta TBT means it will be like this. Okay. The duration is TB or TB equal to 1 by R. Okay. Now if I take the Fourier transform, that means we know that for delta T on the right hand side, it will be 1, and Pt delta T minus delta TB, this Fourier transform, it will be coming like this. Just let me explain it, what it is basically. Say you have a continuous time signal, you have a, this is Xs, okay, for which this is your, say, some xt, this is your xt, okay. If you just sample it with like this, okay, so with some delta T minus kts, then what will happen, it will be the pulses that will be like this, then again, so this one like that, it will replicate, but please remember, if this duration is T, this this replication, this will be 1 by t. Okay, similarly again 1 by t, you will have another pulse. So that actually, that I am just doing this thing. That is P f, that is I am replicating f n minus rb, because it was tb distance apart. Here it is rb distance apart. P f minus nrb. Okay, Pf minus nrb, 1 rb, Pf plus 1 rb, Pf minus 2 rb, like this. And also there will be a 1 by t term will come. This is quite standard proof. You can do this thing actually. Okay, for xt if you do xa, for delta t also if you take the Fourier transform, you will get another pulses. Okay, which is also an impulse train. If you multiply those two, there is convolution in multiplying this one in convolution in the frequency domain with those impulses, you will find this replicating impulses of replicating frequency response of the continuous time signal. So from here, that you will define that if you just take Tb this side, Pf minus nrb equal to this. Now you see that means what we are doing, that I am the spectrum between, say this is f is in hertz. I am considering that I am taking the spectrum between 0 to rb. Okay, between 0 to rb means so that means that I have, now you see that means the original spectrum, say it was like this. Now again at rb, about rb I have another spectrum, same. Again at 2 rb I have another. I have minus rb, I have another spectrum, because continuous time spectrum only pt spectrum was say like this, some pt. Okay. Now that I am just considering between 0 to rb, that means I am considering between in these two, because we are interested between this. So in this one only I have this spectrum and this spectrum, that means Pf spectrum and Pf minus rb spectrum. That is there. So what I am doing, that means I am taking the summation Pf and Pf minus rb. Rest of the n I am not considering, because I am considering f 0 to rb. Now if I just put x and just change little bit with notation, so it will be like this. That means if I take x equal to f minus rb by 2, that is x plus 0.5 rb and x minus 0.5 rb, and I have, and please remember that this pt is a real pulse, and if it is real pulse, then what about pf? Pf is equal to p star minus a. If you do the Fourier transform and do little bit of analysis, you will find that that means the absolute magnitude spectra will be even function of f, and phase spectrum will be odd function of f. Okay. So if I do this, that means this one I can write it as p star of this negative rb by 2 x. Okay. Now with this one, rather here I am assuming that Pf, that means here I am choosing a real pulses, but I am choosing that Pf is also, if we choose, please remember, that is in general for real value spectrum, for real pulses, your spectrum will be complex value, because that's why that star is given. But if you choose the pulses in such a real pulses, so that Pf is also a real value and positive. Okay. Then what will happen? That means that I can write that this, if it is real value, star is gone, means star means because real value a star equal to a, and I can take the mod. Okay, I can take the mod individually, because for real positive, and also I am taking the real and positive. Okay, so it doesn't matter. I can write this. Okay, now I can see that means this mod pf. I can show mod pf maybe of this form. Okay, so now if mod pf is this form, then what will happen that I have my bandwidth. What will be my bandwidth? Bandwidth will be this minimum bandwidth plus RB by 2, and from there RB by 2 plus this fx. I have taken some amount. I am assuming after that this is 0. Okay. Now that means 0.5 RB plus fx. Now, so what is my, and I am assuming that let R be the ratio of this excess bandwidth fx. This is called this fx. This is called the excess bandwidth over R, because minimum bandwidth was RB by 2. So excess bandwidth was fx, and I am assuming R is called roll-off factor. So it is excess bandwidth by minimum bandwidth. So fx by 0.5 RB, that means 2 into fx dB. Okay. So now you see that fx, this fx, that means this side and this side, this fx cannot be more than RB by 2. Fx cannot be more than RB. When fx equal to RB by 2 means what? That means it will go up to like this. Then only fx will be RB by 2. So fx maximum is RB by 2. So then, if fx maximum is RB by 2, that means then R will be maximum value is 1. Otherwise, the minimum value of R is 0. So this is the case. And in terms of frequency, so that means theoretical minimum when R equal to 0, it is theoretical minimum bandwidth RB by 2. And if it is when R equal to 1, then I have R equal to 1, then it is RB. Okay. Now, what is my then the actual bandwidth of PF? Actual bandwidth of PF is basically RB by 2 plus fx. Now, what is fx? Fx equal to 0.5 RBR. 0.5 RBR. Okay. So that means 1 plus R RB by 2. This is my that. Roll-off factor, and that means if R equal to 0.5, that means that if that means R equal to 0.5 means that 50% higher than theoretical minimum. Okay, R 50% or 0.5 means that means 50% above this minimum. So that means your PFE bandwidth is up to 3R by 4. That is R by 2 is minimum. That after that its situation means R by 4. That is that R by 2. That means your total PFE is like this: 0 to 3 RB by 4. Okay. Now this one, that means that bandwidth now PF is restricted in the range of RB by 2 to RB hard. That means this is your minimum bandwidth, and it can go up to this like these dotted curves. Okay, and that if the pulse can be generated as an unique impulse response of the filter with transfer function PF. That means if I have this PF, then I can calculate the PT. Okay. But if you see, that means so my basic type was like that. So that means what I did, I have made a 0 kind of thing. But if you see, if you just read the Paley-Wiener criteria. Okay. Paley-Wiener criteria says that if your spectrum, say if some small range, if the spectrum is perfectly 0, then you cannot calculate the PT. Okay. So that means you have to do some approximation. That means it will not be 0, but it will be some small non-zero number. Here also, then it will be symmetric from this side to that side. Okay. So with that approximation, say we are defining PF equal to 1, and Paley that is therefore unrealizable. That means, but because PF equal to 0 over a people, it violates the Paley-Wiener criteria. and is there the part. Generally we can realize by a practical filter, that is one family of the spectra, that is I am choosing the PF as, that means it is RB by 2 minus Fx, when mod F is RB by 2 minus Fx. Okay. That means I am choosing this is 1, then this side is 0, and when mod F minus RB by 2 is less than Fx, I am choosing something like this type of things. And that means this, and with the different values of Fx, that means when Fx equal to 0, when Fx equal to RB by 4, when Fx equal to RB by 2, that means I have this type of pulse, this type of frequency response, and this type of pulses. It is like a sync, but with some modified kind of sync, looking like a sync. Okay. So and if you play a little bit with this one, that means you will find that is PF. If you play a little bit, PF is something like that. You have a this rectangular functions and with some cos square term. Okay, if you play with these things actually. Now means 1 minus sine 2 theta is to cos square theta, 2 by 2 is gone, cos square kind of thing. Okay. So it is like that it is coming. Okay, so this is called that we say it is a raised cosine characteristic, because it cosine raised to its by its peak amplitude. Okay. Now, and that equation 7.35 is also, that is full cosine roll-off characteristic kind of. Now, if you take the PT, and if you plot this is PF, and you see that I told that PF should be, I will choose PF as real value, and PF should be positive. That we are saying that is cos square term, that is a positive and it is a real value. And PT also I am choosing, that means this is sync function, but with PT I have chosen only real value. Please remember, PT I have chosen only real value. That's why I have taken this one. I have PT is real pulse, I told, no positive business. But PF I have chosen real value and positive. I have assumed. Okay. So that's why that I have got PF like is real and positive, PT is only real. So I have a sync function with some cosine term. Okay. So this is and your finally if the receiver that it should form the zero ISI. That means if I have this type of pulses and as the channel is not ideal, that should be shaped so that the passing through the channel with transfer function they will receive a proper shape, that means such as raised cosine pulses at the receiver, and the transmitted pulse should be satisfied like this. Okay, so now if you so determine the percentage. Let us take this example, pulse transmission rate in terms of the transmission bandwidth Bt and roll-off factor R, assume a scheme using a Nyquist Criterion. So what is my RB? RB is basically that 2 by 1 plus R into Bt. Bt is the, so that means pulse transmission rate varies from 2 Bt to Bt. Now, so now, if you consider that means say Nyquist Criterion. Nyquist Criterion means I have to remember that at 0 time I have a effect and at plus minus NTB I don't have the effect. Now, what is my, if you can remember from 7.33, That means what is my bandwidth of the pulses? Bandwidth of the pulses was 1 plus R RB by 2. That actually that they have taken 1 plus, that is VT2 by 1 plus R. Now that means if I have the if you are using more bandwidth, so that means it may be a little slower to VT to VT, and a smaller R gives a higher signaling rate. That means, and what pulse decays slowly. Please remember that if you choose R small, okay, that means it will be that means when you are here R small, then you will have some sort of a faster pulses, like almost like a scene, but it will decay slowly. But when you roll off, when R equal to 1, then you are sending the pulses are like this. Let me say this one is this particular one. So that means if you see that pulses are decaying fast, so even if there's a jitter or sampling instant problem, then also I don't have any problem, because otherwise that what will happen, that means if you are restricted to this range, then what happened that say you are doing the sampling again at here at this point, something like this. And if you see that, if there is some jitter, what will happen with the same pulses? Say if you are sampling by mistake here or here, then you have lot of effect of this one. Now, but if the pulse itself it becomes decaying fast, then even if you do little jittery sampling, that will not also create much problem, because the ISI will be controlled, because your pulses are itself decayed very fast. Okay, so that's why we are talking about all these things. Okay, so because that sink actually decays very slowly. Okay, so that means, and this is called some sort of a pulse shaping. Okay, now next we'll. So till now, let us stop it here, and tomorrow we'll talk about duobinary pulse. But one important point I like to ask you, that means I like to inform you that we'll have 3 class tests or 3 tests, and because that is the minimum I have to take, and these 3 tests, the date is already given by the department. Do you know the date that the department has already given or circulated in some other courses? Okay, so I will try to find out the mail circulation. That means the department has it is something end of February somewhere actually. So you have another 20 days time. So and it will be most probably up to demodulation will cover. Okay. So now this controlled ISI or partial response signaling, that basically here we are defining, that means so Nyquist criteria requires a bandwidth which is somewhat larger than the theoretical minimum that we discussed. That is your R will be between 0 to 1. When R equal to 0, then you have a theoretical minimum, you don't have any excess bandwidth, but when between say R and R 0.5, then 50% excess bandwidth, and but I have to reduce the pulse bandwidth, because unnecessary increasing the bandwidth of the pulse, you understand the problem. Okay. So now that means say how will you restrict the bandwidth? You have to widen. So that means widen the pulse and narrow the bandwidth. This is the standard idea. Now widening the pulse means that interference with the neighboring pulses. Now that means a known controlled amount of intersymbol interference may be possible to remove or compensate, because there are only few interference patterns. Now I am considering say something like that, P of the pulses, P of NTB, when n equal to 0 and 1, then it is 1, for other L, N, it is 0. That means, see, here, what I am doing, these pulses earlier, if you can remember, my pulses were like this. Now I have shifted the pulse. Okay. What I am doing, so that means that when I have shifted the pulses, the peak is at TB by 2. So I have given a TB by 2 delay. So at n equal to 0, I have 1, here I am taking 1, and at n equal to TB, again I am taking, this one is 1. Okay. Now 2 TB, for this one it is 1, but you see that for 2 TB it is 0, 3 TB it is 0, 4 TB it is 0, like this. Okay. Now it is like that, and similarly this one, you see that, so that means what you try to understand, that individual pulses I have at 0 and TB, for this one TB and here 2 TB. So similarly if I draw another pulses, that means here, that means TB and 2 TB to 3 TB, here I have a peak. What I am doing, I am something like this. So n equal to 0.4. Now this leads to a known controlled ISI from kth pulses to the very next transmitted pulses. Okay. So if we use the polar signaling by, that means 1 is transmitted by PT and 0 is transmitted by minus PT. Okay, because this is I am doing a polar signaling. Now if you play with these things, that means say I have a information sequences, that means 1, 1, 0. This is my actual bit sequence or information. My information sequence. Now you see, that means PT has 0 values for all n except n equal to 0 and 1, and its value is 1. That at n equal to 0 and 1. Figure 7.15. That means this one. Okay. Now you see, consider two successive pulses located at this one. So if both pulses were positive, the sample values of the resulting signal at t equal to TB. So that means here if you sample, then what will happen? That means addition of this and addition of this, that means it will be 2. Okay. That, and if both pulses are negative, so be 2, and if both pulses are negative, then it will be minus 2. Now if the two pulses are of opposite polarity, the sample value will be 0. Okay. And that means what I like to say, I am choosing the pulses a bit delayed version, but I am sampling at this point. Okay, I am sampling at this point. These are my sample points. So when two pulses are of same polarity, then here, rather I am explaining here. That means this is 1, this is 1. That means my at PT minus TB, that value will be 2. Here, say if I have a negative one, then that means say here, say 0 to TB in 1. Here I have some negative one. So if I have a negative pulses like this, then negative means minus 1. And if I just connect this one, so it will be plus 1 and minus 1. Here it will go like this. So finally I have 2 minus 2 and the sample value will be 0 with only these 3 possible values, the signal sample. That means if you see, that means see the sample YKTB 2 minus 2 0, so like this it will come. Now that means the decision rule at the detector, please remember when you will find the decision rule is that the detector, that means by seeing this YT, say I am assuming there is no noise, you have to, that means if the sample value is positive, the present bit is 1 and the previous bit is also 1. Okay. Now if the sample value is negative, the present bit is 0, previous bit is also 0. If the sample value is 0, the present bit is the opposite of the previous bit. So now these from there actually I will do the decoding. Now if the sample value is positive, so first one I am considering, so second one sample value is positive means first bit is 1 and previous bit is 1. That means if the sample value is negative, the present bit is 0, previous bit is 0. That means it is negative, present bit is 0, previous bit is 0. This one is also like this. Now if sample value is 0, then the present bit is opposite to the previous bit. That means if here this one, that means the opposite of previous one. Okay. In this way, we just 0 means here it is opposite of this one. In this way, we are just detecting the sequence, and you see that means this sequence is please remember, this is the bit sequence. From there I am just sending this YKTB. Now YKTB actually it is, at least I am sending this type of pulses, the continuous pulses. Again, this detected sequence means at the receiver there is no noise in the channel, and I am assuming I am just detecting at the receiver, and detecting means I am sampling at 0 TB, 2 TB, 3 TB like this. But I am sending one by one all pulses, continuous time pulses. Okay. So from there I am trying to understand that finally, that means here, see, please remember, though he has said it is one kind of thing, you can say some any other value, something, say some L or anyway, anything. It is not necessarily it should be 1. It's L, 12, minus 12, something like that. And you will get a detected sequence, and you will see that you can detect the cases. So now the Pt goes to 0 at t equal to minus TB and plus 2 TB. So pulses going to 0 minus TB to plus 2 TB. Okay, so that means the pulse, if you see that pulse width is basically 3 TB. Yeah. Now in the previous case, what was my pulse width? The minimum bandwidth one. That pulse was minus TB to plus TB, 2 TB, but here I am choosing pulse is 3 TB. So that means I have made a pulse width wider. Okay. That means earlier it was 2 TB, here it is 3 TB. That means it is 50% higher than the first criteria called the minimum bandwidth. The pulse broadening in time domain leads to reduction in bandwidth, and this is the second criteria proposed by Nyquist. That means the Nyquist has 2 criteria. Please try to understand. Nyquist has 2 criteria. One criteria is that, so these 2 criteria is to limiting ISI. Okay, the first criteria is that limiting ISI means what you have to do, that means I have to choose the Nyquist acid zero ISI by choosing a pulse shape that has a non-zero amplitude at its center and zero amplitude at t equal to plus minus nt. Okay, this was the first criteria. And the second criteria, and then we have chosen this type of, we have seen that this type of pulses, so I don't have ISI and all these things, but for this one is a not unrealizable problem of this thing function, because though it attains the minimum bandwidth, but another problem is that this is the basic thing is that please remember that this is the basic problem, that decaying at 1 by t. Okay, now decaying 1 by t means there's a problem, so that's why what we have done, we have just that we have increased the bandwidth of the pulses. That means initially it was minus RB by 2 to plus RB by 2. Now it is we have given an excess bandwidth. Now you see that, and we have shown this type of example. Earlier the bandwidth was like this. Now the bandwidth is, that is increasing the bandwidth means your sharp decay kind of thing. Okay, now sharp decay is essential, but again, and we have seen that these are raised cosine characteristics. Okay, and because justify, if you see this PF, that PF is something like that. That means you have a rectangular one with some cosine effect actually, cos square effect. That is rectangular one with some cos square effect. So now, actually we are talking that Nyquist criteria is a bandwidth somewhat larger than the theoretical minimum. So rather we want to further reduce the pulse bandwidth. Now in that way we want to widen the pulses, widen the time actually. Now for this one we have done something like this. We have defined the pulse in a bit different way. Okay, and from there we have seen that if we do the polar coating, and finally we have got that we have the pulse duration is 50% higher, because that leads to reduction in bandwidth. But I have the scheme, the ISI is controlled, and this is called correlative or partial response scheme. Okay, this is called the correlative or partial response scheme. So let us finish here. And next class we will talk about this example of Duobinary pulses. Okay. So please remember that exam will be at the end of February, and please read it. Read the book. This is BP Lathi. I am really moving a little fast. So as you have already covered signals and systems, I am assuming that you know the formula. But this formula you please try, because the exam will be all problems, okay, and some small theoretical part will be there. So please try to study, try to do the derivation by hand. That will be helpful in the exam. Thank you.